Let's quickly touch on how ocean can take up additional carbon. This is always about additional carbon. Ocean is already a sink, and we want to find places where additional carbon can be pushed into the ocean. So this is showing a map of surface nitrate concentration in micromoles per liter, and you can see there is high nitrate concentrations in the Southern Ocean and up here in the Gulf Stream and the Gulf of Alaska, North Pacific region. Okay, these uh, symbols here of plus and plus with the red and plus with the a green are places where there is potential for driving more photosynthesis as a process of drawing down carbon dioxide from the atmosphere, additional carbon dioxide. So this is an upwelling region where wind diverges water away from the equator because of the rotational effect. You can see my podcast on upwelling. And that upwelling brings nutrients and drives primary production or photosynthesis by algae. But there is unused nitrate left over because it turns out that to use up all that nitrate, you need other micronutrients like iron. And if there is an iron deficiency, either because there is not enough deposition from the atmosphere or there is not enough dissolved iron coming up with the upwelling water, then the idea is that if you go and dump artificially some iron, which becomes bioavailable, then you can drive additional photosynthesis. This was proposed, already tried, and in fact additional photosynthesis is possible, but it became controversial basically because the phytoplankton that grow with that additional iron weren't necessarily sinking out of the system, because you want iron to be sinking out of the water column into the bottom and get sequestered. Otherwise, if it gets recycled, then it's just going to come back out as carbon dioxide, only temporarily taken up by photosynthesis. Plus, it also drove other processes like additional phytoplankton blooms being grazed by phytoplankton or being uh, digested by aerobic microbes in the ocean, which reduced oxygen and so on. So it wasn't clear if it was a sustainable way to continuously drive increased carbon dioxide into the ocean. Okay, so there are places where iron and phosphorus are limiting, like this one here, and there is experiments done where either iron was added or iron and phosphorus were added, or natural processes of photosynthesis and uptake of carbon were observed. This is from the New Zealand NEVA agency. So this is distribution of nitrate in the surface ocean, showing elevated concentrations in the three HNLC regions. They are called high nitrate, low chlorophyll region, basically because they have unused nitrate that's been brought up by the upwelling or other processes. Equatorial Pacific and subarctic Pacific up here. Overlain are white crosses that indicate locations of the in situ addition experiments with iron and phosphate, and natural iron supply studies. Dust in the air, for example, or going all the way from western Africa over to these regions, carry some amount of iron in them. They are either deposited as dry deposition because of the weight, or as wet deposition with the rain. very high uncertainties in terms of how much of that dust is actually iron, how much of that iron is actually soluble, how much of that dissolved iron is bioavailable for photosynthesis, and so on and so forth. Okay. Nonetheless, Koreans, I think, have, this should be actually from another paper from a Korean group. Sorry, I think I put the wrong one here. Have plans for doing this. I think they've already done it several times, and they're going to do it again. For a while, there was an effort to say iron fertilization should not be done because Canada gave permission to a private company to do it, which was done without any scientific monitoring, etc., etc. But nonetheless, in the Southern Ocean, there are these so-called eddies, which converge surface waters and push nutrients down. Typically, such downwelling eddies tend to be not very productive, but eddies have a way of mixing up nutrients that are different than the general processes of heat uptake and so on. In any case, if you add iron and measure additional CO2 going in, then you can also monitor how much carbon is actually getting exported with a sediment trap, they're called. So you can measure organic carbon or inorganic carbon going out of the euphoric zone, or the zone where primary production happens and respiration happens. Other measurements are shown here with a ship measuring currents, temperatures, and depth, so pressure, salinity, and currents are corresponding to salinity and temperatures, and so on and so forth. Okay, and satellites also monitoring atmospheric input of iron and so on. So it's not out of the contest for sequestering additional carbon yet, but it isn't clear what its full potential is in reality in terms of sustaining the effort to drive more CO2 sequestration into the ocean. But it is a method of geoengineering in general. Now, other than afforestation and ocean uptake and some land uptake and so on, we need additional sources of storing carbon dioxide removed from the air. Okay, so this table shows possible chemicals and building materials that can be made from CO2 and the maximum amount of CO2 that could be utilized. So these are the carbonate materials, chemicals and fuels, and durable carbon materials, approximate market size in terms of gigatons per year, and CO2 demand, and the resulting CO2 abatement or mitigation. So binders and cement. Cement is one of the high emission industries where limestone is heated and broken down to produce coke, which releases the CO2 from the limestone. So we will see in a table what is generally the Portland cement. The method of producing cement has potential of 4 gigaton carbon per year, CO2 per year. That was the estimate in 2016. CO2 demand is 0.1 to 1, and the abatement is unclear in terms, but there could be indirect effects at this scale. Aggregates, so non-metallic minerals are involved. Waste streams have the CO2 demand in terms of the emissions from the process of producing carbonate materials. Reduced emissions likely, negative emissions possible. Okay, so commodity chemicals, fuels, durable carbon materials like fibers, nanotubes, graphenes. So you can see that the size of the market here is fairly small, and the CO2 demand is uncertain right now. It's unclear in terms of the direct benefits, but there may be indirect benefits. Okay, so estimates in this table are highly uncertain. So this is just to keep in mind that conceptually there is this possibility of using chemicals and building materials that can be made from CO2. The CO2 source itself will matter as well. If it's captured through bioenergy and other things and liquefied and supplied, how far it has to be transported, what is the life cycle of the whole process, etc. have to be monitored as well. So this is a general constituents of ordinary Portland cement in percentages by weight. So lime, which is very dominant, is something that can be weathered using CO2. So it's like putting Pepto-Bismol essentially, and there are the other constituents like silica, alumina, iron oxide, magnesia, and so on and so forth. So the idea of cement is basically something that is a combination of these chemicals, and when it's mixed with gravel and sand and so on, it forms a new structure, concrete, which is very solid and is used for all sorts of building constructions, bridges, roads, dams, houses, etc. And if you can pump CO2 into it and it can hold it for a while, then obviously that could be a good target in terms of storing CO2 that's captured from the air, because those buildings stand for a long time when they're built with proper codes for the region, like to withstand earthquakes, for example, or marine weather and whatever else. Okay, so here it is a graph showing the functionalization creation of CO and CN and CC bonds, carbon oxygen, carbon nitrogen, and carbon carbon bonds. Since CO2 is a low energy form of carbon, it's already oxidized, doesn't have much more energy left. Energy must be added to chemically reduce the carbon molecule in order to make organic chemicals that are used in products and fuels today. Reduced CO2 is what is produced by organic or life forms that can produce carbohydrate. So that is reduced carbon, like methane, methanol. Formaldehyde is right here on 0 in terms of the oxidation state of the carbon. So when it's negative, it's reduced. When it's positive, it's oxidized. So this is renewable waste gas production, methane, MEOH. I should have looked it up, but nonetheless, these are processes to which by which CO2 can be formed in reduced forms which have high energy density. This is the Fischer-Tropsch process. Synthetic fuels can be produced, organic molecules and inorganic carbonates. So you can have organic synthesis, hydrogenation, mineralization, dry reforming, electrolysis, photocatalysis, and thermochemistry. Okay, so this is an indication of how CO2 utilization can also be done for producing fuels, synthetic fuels, and other organic molecules. Okay, so that's one way of hiding away the CO2 that's captured from the air. We will look at other examples soon.